Hello everyone, welcome back. I hope you enjoy your fall break. And this week we started our Lab 5 register file. Okay, go to our website as usual and you can find our projects here. For the past week, I have to change the background of the week, so you can see, you can find this week is week 10, is on Lab 5. The PDF is our instruction, and you can download the ISE file, and this is the project you can work on. Okay, let's see what's the task for Lab 5. So Lab 5, we will learn the register file. And during the class, I think you already learned the register file for the MIPS CPUs. But for our own CPU during the lab, we have a tiny version of the MIPS register, so which means it's much easier than the MIPS register file. And here is the instruction to how to design the register file, and just to point out that this is the system we want to design for the Lab 5. We have two modules, the register file and the ALU. ALU is exactly what you designed last week for the Lab 4. And the register file is what we designed this week. So let's see. After you download the folder Lab 5, unzip it. Don't forget, unzip it and open the folder, find the projects file, double click, and then you can open the ISE project. And there's a lot of blanks for this project, and so don't worry, I will show you what you need to do for this week. On the left, for hierarchy window, you can see the test bench and the top module. And name the top module as CSCE2214. And in this top module, we have two separate modules, sub-modules. One is ALU, one is register file. And first, we open the register file. So double-click register file, and here is the register file. For a register file, there's only two outputs and several inputs. And for detailed instructions for this definition, you can go through the PDF file and you will read it, you can know it. And for easy version, you can see we can give the B and C address and read from the register file B and C data here. And the A address and A data is the value we want to write into the register file. And the address is the register number. Okay, and the first step, we have to define the register file. According to my lab session, if you came, so you know that I told you that you can think about the register file as an array. And the first step, we define a new type. It's called RAM type, and the type is array. And there are 16 elements in this array. Each item is a type of standard logic vector, and there are 16 bits for each. So in this array, there are 16 items. Each one is 16 bits standard logic vector. So this is our new type, RAM type. And then we define another signal named the register file and define as the RAM type, which we defined just now. So then we have a register file, and its name is reg_file file. So you can think about this is our array. And in the process, the first step is to initial all of them. So we have 16 items in this array, so it just gives 16 bits zeros for each one. If you like, you can Google how to use the for loop in HDL and make it easy. But here I just give you all of the case from 0 to 15 and give them zeros. And after that, so here this part is how to write into the register file. If we have the clocker edge and the load is 1, we write the data, A data, to the register file. The index number is based on the A address you give to this module. And after this part, we make sure you don't write into anything to the 0 and 1, because the R0 and R1 is predefined, it is always equal to 0 and 1. So here is make sure you don't write into the R0 and R1, because they are read-only, they cannot write into it. So after that, after the process is the read from the register. Based on the address you give to B and C and the data in this register file, or you can say in this array, you'll read and give it to this B data and C data as the output of the register file. So that's the value or the meaning for this register file. And if you want to see the example, you can go to my class during the lab session, and I will give you the example. So then double click the ALU top module, and this is our top module. So don't worry, the ALU, and I have already gave you the ALU code in here. So and the second, so this is the ALU module. So that's exactly what you have for Lab 4. Okay. Yep. So let's go back to the top module. So the top module for the CPU have two modules defined, ALU and a register. And the next step is define the signal you need. The cout is the cout signal for the ALU. Opcode RS, RT, RD is based on your instruction. Sout ALU is the output of ALU. RS data, RT data is the data we read from the register. Okay, so by the way, if you cannot see it clear, you can change your resolution of the YouTube video to the 1020p, because I changed my video to make sure it's the typical 1020p, so it's clear. And if you think I'm really running too fast, you can just click the pause and just to see clear what I have here. Okay, let's go on. So the first step is instruction fetch. So whenever you have a 16-bit instruction, to be clear, our CPU is 16 bits. The CPU you learn from the lecture is 22 bits, so they're different. We are much easier. Okay, so 16 bits each instruction, 4 bits for each field. There are 4 fields: opcode, RD, RS, RT, and each one is 4 bits. So you can here we break down the instructions and give the appropriate fields to the appropriate signal. And the second one, based on the instruction we have, we can just initial the register file. The clock is clock, clear is clear. Okay, A address is the address we want to write into the register, so the address is RD. And the output is Sout ALU. And for this time, for this lab, we give the load for 1 because we always want to write into the register. And B address is RS, C address is RT. And then B data is RS data, C data is RT data. So that's how we initialize the register file. And then for the ALU, you already know how to do that. So the A is read from the RS data, B is from the RT data. For this part, the selection signal for ALU is from the opcode. So that is how you can control which operation you want to run for the CPU. Sout is ALU Sout, and cout is a cout. So for this part, the Sout ALU actually goes back to the register. So for this type, we can typically create an R-type instruction CPU. So if you don't understand, just find me and ask me. I can explain it more to you. So the memory and the write back is not for this lab. We will extend it later. So let's go to the test bench. So for this test bench, I have already gave you some the comments for the register you need to test. And the first one is the example. You have to translate this instruction to the hexadecimal number. That is much easier than the MIPS instruction. So we have 4 fields, 1, 2, 3, 4. Each one is 4 bits. So we need 4 hexadecimal number to present each field. First one, addition the opcode is 0. R2 is number 2, R1 is number 1, R1 is number 1. So 0211 is the corresponding hexadecimal for this instruction. It's pretty easy. You see, that's much easier than the MIPS instruction. So I gave you the blank rest of them so you can figure out how to translate the instruction to the hexadecimal number. After that, and swap the tag from implementation to simulation to simulate it. Okay, let me show you what's the final results. So after you simulate it, it's running like this. So first step, don't forget to change the instruction to hexadecimal number. The radix hexadecimal number, and you see here is our instructions. And for the default signals we have, there's nothing for the output because the CPU actually right now is enclosure, so it's not open system. So actually we want to see what happened in the register file. So how to do that? Okay, please pay attention to here. So last semester, a lot of students cannot figure out how to add this signal into the wave. So on the left part is CPU test, our test bench, and in this test bench we have there's our CPU. In our CPU there are two modules we instantiate. One is ALU, the other one is register file. Click the register, and here's the object name is list all the signal you have in the register. And the last one is the register file, is the signal we want to monitor. So we just drag the signal to the wave, or you can right click here, add to wave window. Okay, either way. After you add it, change the radix to signed decimal number. Okay, signed decimal number. And click the arrow beginning, and you can see here are 16 items. There's a 16 register. Okay, click the shift to choose all of them, change the radix again to signed decimal number. Okay, so we have 16. So you see here's some values here actually. So let me just restart. Click here to restart the simulation. Because we add more signals, so the simulation have to rerun. So click the reset and then click here for the run. Okay, and click the third amplifier so to make the sizes easy to read. Okay, click your cursor to here, the first instruction. You see at the beginning the register file is 0, 1, all of them is rest of them are zeros, so that's what we need. But for first instruction is 0211. We want to read from the register 1 twice, add them together, and write into the register 2. So you see 1 plus 1 is 2. So after this clock cycle, the clock raising edge, for this instruction, the register file number 2 is changed to 2 because originally is 0. So that means your CPU is working. Okay, so you have the challenges to check the rest of them. Okay, so that is this is for the lab 5, and the same thing for fill in the blanks for here. So tell me each part, so the value for each part. And here I just give you 2 bits. You can give me 4 or 2, doesn't matter. And the value is read from your wave. And give me a screenshot for this table and the wave. My screen is small, but make sure you can put everything into it, especially for the register file. I want to see this, okay, this value. Okay, that's lab 5 for register file. So good luck for everyone. See you next time.